And hi, let's get started. So in the last video, I actually talked about the three modes of nuclear decay and how gamma decay and alpha decay they can be readily explained by the Schrodinger's equation because they rely heavily on the wave nature of matter. Okay, beta decays are their own special sort of decay because they rely on the weak nuclear force. The example I gave last time was the example of cesium 137, and one of the ways it decays, because there are multiple ways, that one of the ways it decays is through um, beta decay or beta minus decay. Okay, I just want to make sure my pad is working. So, beta decay is very, very different from the usual usual modes of decay. Okay, so anyway, I want to save this as lecture, or rather rambling lecture, whatever. Lecture number 9. Number 9. Okay, I'll save it and let's focus a little bit more on beta decay today. Well, where is this? Freehand. Beta, no, I shall use blue. Beta decay. And I want to specially highlight the weak nuclear force. Okay, so why is it called the weak nuclear force? Okay, or why is it called the weak nuclear force? So for context, let's go back to maybe the helium atom. Oops. Okay, so this shaded one's going to be like a proton. The unshaded one's going to be a neutron. Uh, then you have okay. Let's use the wave picture. So I'm going to use maybe this sort of electron. Okay. Okay. The wave function may not look like this, but I want to draw it because it looks like a wave picture. Okay. So you have an electron cloud moving over it. Electron cloud. Okay, and for some reason, okay, this is a minus, this is a plus. So there is some attractive force that holds these electrons in place, but they do not collapse into the nucleus, probably because of some quantum effects. So what those are, I'll leave it to the physicists to explain. Okay, so this is the only force keeping it in place. Now, if the electron, okay, the electron could sort of go into the nucleus a bit. Okay, if the electron will be to so-called be close to the nucleus, and if there was a strong nuclear force, if because the strong nuclear force is actually holding these protons together. Okay. Now, if there was a strong nuclear force, the electron would so-called be stuck in the nucleus, okay, because it's that strong. But somehow the electrons are not. Electrons are not affected by the, well, this attractive force in the nucleus. We call it the strong nuclear force. Let me see if I'm speaking loud enough. Okay, it should be fine, the volume level. Attractive force, strong nuclear force. In the nucleus. Okay, so that's one observation. Okay, observation number 1. Yeah, so not all particles are affected by strong nuclear force. Affected by strong nuclear force. Okay, but so some of these are affected by other forces like electromagnetic force, but neutrons are not affected by electromagnetic force. Okay, so the strong nuclear force, okay, we call the particles that are affected by it, we call them quarks. Okay, we call them quarks. So that's in the standard model. Okay, so whatever you have in the nucleus, these are quarks. They are affected by the strong nuclear force. Okay, affected. So just to give you some names, okay, by strong nuclear force, okay, is equals quarks. Okay, so these quarks, they are affected by the strong nuclear force. Okay, to be fair, quarks are what actually makes up neutrons and protons. So neutrons and protons are just collection of quarks if you really want to be so precise about it. But you just leave it as that. Okay, so yeah, that's the more correct way of saying it. Yeah, anyway, I want to say I'll be using the standard model here from OpenStack's LibreText Physics. This is shared by CC by 4.0. So it allows me to use and remix this content as long as I give attribution. So yeah, I can use it even commercially or whatever. So yes, just give appropriate credit, and I'm giving appropriate credit now to OpenStack's. This is the author, and it's from LibreText. Okay, so strong nuclear force is affected. Particles affected by strong nuclear force are quarks. Okay, but not all of them are affected by strong nuclear force. Okay, for the weak nuclear force, there are a few other particles. They are called quarks. I mean, quarks are also affected by weak nuclear force, leptons, and neutrinos. So, I mentioned, yeah, weak nuclear force, it's responsible for beta decay. So let's try understanding how it works. Okay, so what I'm saying is that weak nuclear force, strong nuclear force, electrons are not affected by it, but we observe beta decay. So I guess the way we can sort of weave in this weak nuclear force is, okay, there must be something to explain beta decay, because electromagnetic force is here governing the shape of these electron waves. Of course, the strong nuclear force will affect the way the nucleons, which are protons and neutrons, nucleons are arranged in the nucleus. Again, same Schrodinger wave equation. Okay, so alpha and gamma decay are governed by that. Or you can use the Schrodinger equation to explain these decays. For weak nuclear force, we use that to explain beta decay. So let's do some simple things first. Weak nuclear force. So the thing is that it is a force, right? It is a force. So you can actually have collisions. So for example, okay, I'm going to use this thing called the Feynman diagram. Okay, Feynman diagram. This is a very useful tool used to explain how particles collide. You can see the bottom axis here is position, or x. The vertical axis is time. So what we want to use here is okay, I'm going to write here Feynman diagram. Okay, it's named after Richard Feynman, I believe. Okay, at least that's my gut feel. I could be wrong. Correct me if I'm wrong, but I think it's named after Richard Feynman. So he's all right. It is named after Richard Feynman. He's one of the scientists in the Manhattan Project, and he has a lot of interesting lectures, so you can go watch them in your own time. But I want to just do roughly a Feynman diagram here. So to introduce you to a Feynman diagram, let's consider how two electrons collide. Okay, let's consider how two electrons collide. So electrons are negatively charged. Let's just think of them as particles for now. Okay, one electron goes here and then into something that's so-called so-called stationary, but we cannot say it's stationary. That there are some quantum physics principles that prevents it from being completely stationary. But for all intents and purposes, let's just pretend they're stationary. Okay, so one electron collides into another. So this is like a before, and this is a after. Okay, after maybe they will fly apart like this. Okay, depending on which frame of reference you are looking at, it could be a glancing collision, it could be inelastic, but we try to use elastic collision here. Okay, so this is roughly the way that you kind of do a collision. But of course, this is pretty messy. Maybe let's use something that helps. Okay, so instead of instead of what do you call that? Instead of uh, just having these random particles banging into each other, having a before and after, it is better to sort of use something like the graphical axis to so-called make things a little bit more precise, a lot neater. So instead of a before after picture, you have a time and x-axis. And so let's say two electrons are again here, electrons are again here, and they start as time goes by. So as time goes by, they start moving together. Okay, so of course in this picture they are stationary, but if you change your frame of reference, so to speak, that means if your camera is moving along at some certain speed, from another point of view, you could of course see them as moving towards each other, and that's what we call the um, center of mass. Okay, center of mass, or sometimes abbreviated as CM, frame of reference. So no math here, okay? No math. Okay, so if your camera was so-called stationary and both of the electrons are just bumping into each other, and after that they will fly off like that, more often than not, okay, you will call this the center of mass frame of reference. So I think that's a useful picture to have. Of course, there are more nuances and details. I'm skipping out a lot of them, but just bear with me, all right? Okay, so two electrons are moving towards each other. Okay, and after some time, they will bump and fly apart. So this is the so-called trajectory, okay, of them bumping into each other. Okay, if we were just to think of them in terms of two billiard balls or two ping pong balls bumping into each other, this is the picture. However, in the quantum world, it's a little bit more complicated than that. Okay, what we like to do is to say, okay, instead of the repulsion of the electrons causing them to bump apart, I mean, yes, there is repulsion, but there are particles that actually so-called help mediate this repulsion. So for electromagnetic force, we actually have a photon. Photons mediate the electromagnetic force. So I'm not going to go into the weak nuclear force yet, but I'm going to start us off with something more familiar. Okay, you have two negatively charged particles, they want to fly apart. Sure. Now let's have this idea that, okay, particles actually transmit force between uh, these two electrons. So in the electromagnetic force, this particle is a photon. So what happens here? What happens here is that this electron will emit a photon at some time, and this photon actually carries away momentum. So this is a photon. A photon. Photon is a particle for light and is an electromagnetic wave, however when you think about it. But in this case, it's very much more useful to think about it in terms of a particle. So your first thing happens here. The electron emits this photon, and because there is momentum being carried away by this photon, this electron now flies away in the other direction. Okay, so this photon is going to meet this electron at some later time. So this is what T1, this is T2. So this photon is going to meet this electron here at some other time and space, and this electron is then going to fly off in this other direction. So in the standard model, this is how we understand collisions. Okay, they are mediated by particles, and that's what you are sort of seeing here. We have this so-called virtual photon carrying away energy and momentum, okay, that carries the force from this electron, this first electron, to this second electron. Okay, so this is how I guess one way of understanding Feynman diagrams. Okay, the true physicists will of course probably correct me a lot of this, but this is how my layman engineering understanding is seeing it based on what I just read. Okay, so right, I want to bring this Feynman diagram here because I want to use this as a scaffold to help us understand the weak nuclear force. So for the weak nuclear force, okay, we have bosons carrying force. Okay, so it's the same way this photon is carrying force from this electron 1 to this electron 2. So instead of the photon carrying force, we have other bosons carrying force. So these are W minus W plus and Z. Okay, very foreign, yeah, but okay, very foreign, but just bear with me. So these basically have the same purpose, to carry force and energy from one particle to another. At least for the Z boson, W and plus and minus actually carry charge as well. So these are more responsible for the decays. Z bosons are more responsible for carrying force. Okay, and just for your information, photon is a boson as well. Is a boson. Okay, so there's this thing about bosons and fermions. They are categorized based on spin, but I don't want to give you too many things to deal with in this video. So let's just call these bosons for now. And bosons are responsible for carrying force from one particle to another. At least for the for the weak nuclear force and the weak nuclear force and the electromagnetic force. Actually, the gluon, is it a boson? I have to check again. I think it is, but yeah, we will just leave it as that. I know the photon is a boson, and of course W plus, minus, and Z are bosons as well. Okay, so this is again engineering and an engineer explaining stuff to the best of my knowledge. I don't know as well as a physicist, but this is just to help you understand what's going on in beta decay. We need some of this quantum background to understand that. So now, instead of an electron meeting another electron, an electron can also collide with this thing called a neutrino. Okay, this neutrino. So the same idea happens here. Neutrinos are not, okay, neutrinos are, okay, neutrinos are, okay, they are denoted like this, this V looking thing, VE. They are neutrally charged, neutral charge, and affected only by gravity. Oh, gravity. I mean, all particles are affected by gravity and weak nuclear force. So if there's a particle that we want to use to demonstrate weak nuclear force collisions, it's the neutrino. Why of course electrons can actually uh transmit weak nuclear force to each other, so to speak, and bump to each other due to weak nuclear force, but usually the charged particles, the charge is a much stronger force, so you probably have this photon collision before the weak nuclear force ever has a chance to really have some significant impact. Okay, so let's do this collision picture, this time with an electron and a neutrino. So the E subscript here, this is what we call electron neutrino, because there are other kinds of neutrinos as well. We just want to make sure this is a electron neutrino. Okay, again, we have this picture where an electron and a neutrino are coming together. Okay, the electron is going to emit something now. Okay, what is this something? It's called a Z boson. So this Z boson is going to carry away, again, energy and momentum. And because of this thing, this electron will start flying away in this direction. And after some time, this neutrino will absorb, okay, this T1 and T2 and T1, this neutrino will absorb the Z boson and will take the momentum and energy away and fly in the other direction. Okay, so this picture is how the weak nuclear force works as according to the standard model. So an electron collides with a neutrino, electron neutrino, because of the weak nuclear force. Okay, so electrons collide with neutrinos cause of weak nuclear force. Okay, so this one's sort of easy to understand. I guess the slightly more complicated part, but also not that complicated, once we see it, okay, not superbly complicated, is that these electrons can pass charge to another particle using these other bosons called the W plus and W minus. So let's take a look here inside this standard model, and let's take a look at this beta decay. Okay, weak nuclear force is responsible for radioactive decay. So in this picture here, we have Feynman diagram. Okay, same Feynman diagram, but we have two pictures here. In picture A, here we have a neutron decaying into a proton. This neutron will emit a W minus boson, and that will itself decay into an electron and antineutrino, which is this V minus thing here. For this one, okay, a proton is combining with an electron, and then they sort of neutralize each other because of the charge, and the result is one neutron and one neutrino. So okay, let's go through this slowly. So this is a very detailed look of, relatively detailed look at what's going on. Okay. Again, Feynman diagram, T and X. Okay, so here's a neutron going across time. Here's a neutron. And instead of having the Z boson, we have W minus boson. Okay, so neutrons are not positively charged, they're neutrally charged, but the moment it sort of decays, it will become a proton. Okay, proton. So this is a plus and a what we call W minus boson. Okay, so this neutron essentially splits in two. Okay, so step one, neutron splits in two. Neutron splits in two Okay, so you have a proton and a W minus boson. So this proton is positively charged. This W minus boson is negatively charged. So there's a balance of charge that happens. Okay, step 2, W minus boson decays into electron and antineutrino. Okay, that's just the way it works. Don't ask me why. I'm not going to go detail into that. That's not my specialty. I want to move into nuclear engineering as fast as possible. So this thing here, okay, it was split into electron and electron antineutrino. We use this overline here to explain, okay, this is the antineutrino, it's a minus on top. Okay, but it's kind of difficult because this antineutrino is not even charged in the first place. So there's no way you can just use charge to differentiate both of them. Like, as in you have an electron and a positron. Okay, both they are antiparticles of each other, antimatter. Okay, so electron is the matter. Positron is the anti-electron or antimatter version of electron. Yeah, you can differentiate them using charge, but with neutrinos, antineutrinos, you cannot. But I mean, okay, live with it. Yeah. So this is the W minus boson, and we just witnessed the beta decay of, or rather, try to use this Feynman diagram to illustrate beta decay of uh, a neutron into a proton and the electron and the antineutrino. So 3 particles. But it's a 2-step process as described in this Feynman diagram here. Okay, so okay, so neutrons, okay, by themselves they are kind of unstable. So that's just something we live with. The half-life, I believe, is about 10-ish minutes. Okay, neutrons are unstable. Lone neutrons, I must say, lone neutrons are unstable. Okay, so they are radioactive. Okay, half-life. Okay, I haven't even explained what half-life is, but okay, half-life is on the order of 10.5 minutes. Thereabout. Okay, so anyway, this is a neutron decay. Okay, so we are using this W boson to explain why it decays. Okay, then yeah. So there is some, every time there's a beta decay, you can see the neutron which was so-called at rest, okay, somehow energizes the proton. The proton has some kinetic energy and the electron sort of flies out of the nucleus. Okay, we call this a beta minus decay. Beta minus decay. Beta minus decay. So this is very much we call beta particles. These are just electrons, or beta minus particles. These are electrons flying all over the place. So this is what we call beta minus decay. Now, can neutrons also decay when in the nucleus? Yes, neutrons can also decay. Can also decay in unstable nuclei, as you saw in cesium-137. Okay, so I think the Feynman diagram you can use is this as well. That helps you to see what's going on. Okay, so let's talk about the other one. The one we see here is called this one is called electron capture. Electron capture. Okay, so let's have electron capture. T X. So it's what? Electron capture. This is also one way the so-called beta decay can happen, but it's not strictly speaking emitting any beta particles at all. So, but it is what happens for nuclear decay. So we have a proton, which is a plus. We have an electron, which is a minus. Okay, what happens here? Proton comes. What does it emit? Okay, we want to say this emits a W plus boson. So it's got W plus. And this thing goes here, it becomes a neutron because this now carries away the positive charge. Okay, so this happens first. This carries away the positive charge. Electron comes in with its minus charge. Okay, maybe I'll use a straight arrows here. Okay, electron comes in, meets this W plus boson. What happens? It becomes an electron neutrino. Okay, electron neutrino. So this is at T1. This is at T2. So this is called a W plus boson. Okay, so this picture does look a little bit more like what we see here. An electron and a neutrino exchanging force due to the Z boson. But in this case, there was no charge being exchanged. Here at the photon as well, charge not exchanged, but we see that force was being exchanged. Over here, there is charge in addition to force and energy being exchanged for both this electron capture process and for this neutron decay process. Okay, beta decay. So as you can see, now this neutron is so-called as excited. So it has some kinetic energy, it's moving elsewhere. So this sort of excites the nucleus as well. So you might see these processes coupled with gamma decays as well, as it was in the cesium-137 diagram. Okay, last one, which is not included here, is important to describe beta plus decay. Beta plus decay. So it's the same thing as beta minus decay, except that you start out with a proton first. This proton is going through time, okay, and it's stationary, so to speak. Okay, and okay, it emits an electron, emits a W plus boson. This W plus boson is somehow supposed to decay into positron. And let me see whether I'm, yeah. Positron plus electron neutrino. This is called beta plus decay. Okay. Of course, this positron doesn't hang around for long. This positron, because it's in a lot of electrons, lying around, it will usually recombine and give you two gamma rays. Okay, these are photons. Okay, gamma rays are just a subset of photons. Okay, high energy photons. This will be 511 keV, if you want to know. But this is what beta plus decay looks like. So if you heard of this is actually quite useful. If you heard of something called PET scans, okay, positron emission tomography. Okay, this is a PET. Okay, this actually makes use of this particular process. So yeah, I've given you a rough picture of what beta decays look like and how they are actually mediated by this weak nuclear force. Okay, so basically these bosons W plus, okay, this W plus boson is also important for electron capture. This one also important, it's for beta minus decay. All of these are pretty important. Okay, so for nuclear decays, usually, yeah, the question is why, okay, how can this W plus boson just exist, okay, and then suddenly convert into this positron? Okay, this thing actually requires a lot of energy, okay, because basically if you have electron capture, there's no positron here. Okay, no positron is missing. Okay, no positron here, and somehow it just so-called annihilates. It instantly combines with this electron and becomes a neutrino. Okay, there's no positron to speak of, no gamma rays, no nothing. Okay, in this electron capture process. Okay, so why does this happen? Okay, the thing is that for this beta plus process to happen and supply this positron, you need to actually supply a fair bit of energy as well. So these proton decays don't really happen at all. So that's why you don't see hydrogen atoms, hydrogen nuclei suddenly just poof, splitting apart into this W plus boson and neutron, or even the positron. So this thing actually needs a lot of energy, and it's a little bit rarer. Okay, it needs a lot of energy. You don't see this process happening as often as, let's say, this electron capture process, but it does happen in some unstable nuclei. Okay, so I want to say this, yeah, some unstable nuclei can supply energy for beta plus decay. Okay, where does this energy come from? Okay, this is partly due to the way nuclei are arranged. We call this binding energy. Okay, so now we are coming back to uh, coming back a little bit more to the nuclear physics side. We need to talk about binding energy, fission and fusion. All of this will start coming in. Okay, so probably talk about that next time. These are fundamentals, fundamental physical process that can help explain why fusion or fission is feasible, so on and so forth. Okay, useful. But I mean, I hope this thing today actually helps you to at least conceptualize how force is being exchanged between particles. Okay, it may be a little bit more too much information, but what I want to say that is that yes, you probably need a more information to study beta decay in detail. This is just the bare minimum. Okay, that there are things that happen as well. These beta particles actually carry away spin and so forth. I'm not going to talk about that. I'm just going to say it happens, and this is just your rough introduction as to what you're getting into. Okay, I'm just going to say this happens. It needs energy. Some nuclei do it, some nuclei don't for reasons. Okay. So how I like to think about this is that, okay, there are lots of quantum effects going on in the nucleus. Okay, I just for the nuclear engineering side, I just accept that these are the case. Some nuclei decay, some do not. Okay, there are physical processes governing it. I don't want to know too much detail. End of story. Yeah, I just accept that this happened and you just live with it. Let's see how we can make use of it. That's the engineering perspective. Okay. Okay, but what's way more important to understand for nuclear engineering is, of course, you need to understand decays to some extent, but you need to understand more nuclear physics. Okay, this is where we have to start going next. Okay, binding energy, mass effect, all of this. Okay, no, as few math, I'm hoping to get as little math as possible, just to give you an idea of what's going on. But uh, yeah, I will just yeah, leave it as that. Okay, and I think I'm also running out of pages here, so I'll probably have to move on to a new PDF thingy. But I'll leave these notes on GitHub as usual. Okay, so I hope this is somewhat helpful to help you visualize how people think of things in the quantum physics realm. Okay, not superly important to understand all this level of detail, but hopefully this hopefully this helps you see a little bit more into how to think about decays, nuclear decays. What are the fundamental forces responsible for all these nuclear things? Okay, so I'll stop here. Thanks for watching. See you guys next time. Bye bye.